Next topic is called as friction. Right. So friction is basically it's a uh, type of force that exists between the two surfaces which are in contact and they try to move. Okay. So that's the force, and obviously this force is uh, tangential. Always there will be a tangential force, right, along the surface, right, opposite to the direction of motion of the bodies. We call it as a friction. Okay, now let us try to write some points. These are the basic points related to friction. So the friction is a tangential component. It's a tangential component of the net force. Net force acting between two bodies in contact. Normally, this starts acting when there is a tendency of relative motion between two bodies in contact, or actual relative motion will take place. So the friction has a tendency to stop the relative motion between the two bodies in contact. So why friction, right? The frictional forces do exist. They try to stop the bodies from moving. Relative motion, right, is going to be avoided. They try to avoid, it's going to be, right, avoided by the frictional. It tries to, right, avoid, right. So when the, if two bodies in contact are not moving, they are stationary, means no friction, but it it starts acting when there is a relative motion between the two bodies in contact. So when they are in contact and they tend to move, the friction comes into picture, which tries to stop the relative. I can add up here. It tries to stop the, the relative motion. We are trying to stop it. If there is only a tendency of relative motion, the static friction acts, and if actual relative motion takes place, there is another type called as kinetic friction. Right, two types of frictions do exist. One is called as a static friction, right, it tries to stop the tendency of relative motion, right. So let me write one point here, that is the tendency of relative motion means the friction which comes into picture is referred to as a static. It's called as a static friction. Instead of the tendency to move, actual relative motion. So if there is actual relative motion, then the friction that exists is called as kinetic friction. All right. Now, we know that there is a concept called as uh, for every force there is a equal and opposite force, right? Like any other force of uh, nature, frictional force also makes pair of equal and opposite forces acting on two different bodies, right? It is opposite in terms of the direction. So the direction of the friction force on a given body is opposite to the direction of the relative motion. So direction is important because whenever we try to write the equations for different types of forces, we follow the convention which is positive, which is negative, right? Decided by the direction of action. So that's why we write another point related to the direction. The direction of the frictional force. Direction of the frictional force on any given body is opposite to the direction of the relative motion. Of this body. All right. Now, right, let's take an example to understand this process. So, let us say this is a ground, and let me place a object over here. Let me apply force in this direction. I'm trying to pull this object to the right, right? So this is the force, maybe I apply T. Now, since the object is trying to move to the right, the frictional force is going to be applied in the opposite direction. So this is the direction of friction in this case. All right. So that's the idea, right? With respect to this object A. Now let's take uh, another case, right? In this, let us say we have a surface, and let us try to place two different objects. This is object 1 and this is object 2. Okay, now let us try to analyze a situation like this. There is a force F1 acting on this body. There is another force F2 acting on this body. Say this is body B, this is body C, lying on some surface. Now you see the relative motion between the two blocks means they have to move at different velocities. That's the plan, right? So the friction comes into picture between B and C only if the velocities are different. If both B and C move with the same velocity, no relative motion. When no relative motion, there is no friction. Okay. In this case, again, since the bodies are moving right, relative motion is to the right. Their velocities are different, right? What is the direction of the frictional force? I can say that there is a change the color. Okay. So the direction of the frictional force is once again in this direction. Okay, this is the friction. And what is the objective of friction now? Not to stop. The frictional force tries to make their relative velocity same, right? Relative velocities, right? The velocity become equal, relative velocity becomes zero. Their velocity same means relative velocity equal to zero. So in the first case, the friction tries to stop the object from moving. But in the second case, right, the friction tries to make their velocity same so that relative velocity becomes equal to zero. Okay, so two types we can see. The first type of friction, which is static, second one is the kinetic. Okay, so we have some notations over here just to follow. So this friction, I'll try to give a notation. Static friction, the standard notation for the static friction, it's called as a limiting friction as well. So this is denoted by FL or FL, both are same. Okay, at the same time, this friction which you see between the two different when there is a relative motion, this is called as Fk, indicating that this is a kinetic friction. All right, now let's consider the values. So for a given system, okay, for a given system, right, the F limiting the static friction, not kinetic. The static friction or the limiting friction FL is a constant. It's not going to change. But the kinetic friction is proportional to a force N, and this N is the normal reaction between the bodies, where this N is the normal reaction between bodies. Now let's look at what is this normal. So that is, let's consider the surface, right? Two different objects. That's the surface, and upon which we have placed a body. So now let's think that the body is trying to move in a particular direction because of some force applied. This is F1. Now, because of the weight of the body, right, this exerts a force, right? So there is a force which is acting between the two bodies. This body pushes the other body downwards, which means the body which is below pushes this upwards. So you can see that there is a upward force. This is the N which we are talking about. There is a normal force N between the two bodies, and if the upper body tries to move to the right side, there is a friction. I'll change the color for friction. So there is a friction acting in this direction. Let me assume this is how the friction acts. Okay, so this is maybe I'll denote Fk, kinetic. Right, now you see, if I try to complete this particular rectangle, maybe just like this, and I draw another component. This is the actual force, the normal force plus this force is this. Now I can see that, right, I can try to find a constant between Fk and N. So that is because, let me try to write, Fk is proportional to N is what we have written earlier. So we know that the Fk is proportional to N. Or I can write Fk is equal to some mu into n. Okay, so that means I can try to write there is a constant Fk is equal to this. So this mu is called as the coefficient of kinetic friction, right? So I can actually find this if I call this is some theta, right? So, and let me say I'm taking the tan theta. Tan of this angle theta is equal to opposite side is this side, that is n itself, right? So the height of that side is n. So this is n divided by adjacent is this side, that is denoted by Fk, right? So this itself is mu. Tan theta is mu now because it's not mu. Fk by n. So I'll write mu is equal to the Fk by n. So I'm having n by Fk over here. So that means I just can write this as 1 divided by mu, right? Theta is equal to tan inverse of n by Fk, which is equal to tan inverse of 1 by mu. You can apply this whenever we require this to be applied. All right, let's move further. All right, now let us try to one quick. Find the normal reactions between the surfaces this is 3 kg, this is 8 kg. Take G is 10 meter per second square. Okay, so the normal reaction between the 3 kg and 8 kg, it's same as the the force that the 3 kg exerts on the 8 kg mass, right? That force is repelled by this one by exerting the same amount of force so that the system is in equilibrium, right? Let me denote that particular force as say N1. Okay, so this is the first normal reaction which we are talking about. It's perpendicular and let me denote this is N1. Similarly, the second normal force that exists over here, this is what I denote as N2. That is the force which the two objects together puts on this surface, and the surface responds back with the same amount of force, so that the system is under equilibrium. Okay, so N1 is nothing but it's just considering the 3 kg that exerts on 8 kg mass, right? So N1 is equal to, I can simply write. It's very straightforward answer, nothing to calculate. So N1 is equal to the mass into the velocity, mass into acceleration, that is 10. So this is 30 newtons. Okay, similarly, when I write N2, now you see N2 is nothing but it's the result of 3 kg plus 8 kg. So this is 3 plus 8 into 10. This is 11 into 10, 110 newtons of force will be exerted, that is between this surface, right? If at all you had another surface below this, all the three surfaces, all the three forces will be added together to get the next one. Okay, then, okay, let's move further. Let's define what is called as the angle of friction. Right. So this is standard notation is lambda for this. So let us try to consider one scenario. Let us say this force is the normal force. This is a frictional force denoted by mu into n, because F equal to mu n, the standard friction. Friction is equal to mu times the normal force. This also means that we already know this. We can complete the rectangle and we can calculate other values as well. So this is the actual net force. This is the F on the bottom. So if I try to measure an angle between the resultant force and the normal, and I denote it by lambda, this lambda is called as the angle of friction. So how do you find out tan lambda now? So if I want to find tan lambda, tan is opposite, opposite is mu n divided by n. So this is simply mu, right? So you want to find lambda, that is tan inverse of mu, right? Using this equation, if you find tan inverse of mu, you can calculate what is called as the angle of friction. All right. Okay, that's the concept that we are going to use. Then we have another concept. This concept is called as the angle of repose. All are related to the friction itself. Now, this concept is derived under this condition. Let us say the surface is tilted and okay, let us say we have placed a body like this. There is a mass m here. Let's say there is a theta. That's the tilt. Okay. Now, so there is a block of mass m placed on an inclined plane with inclination is equal to theta. Now, this inclination can be increased or decreased, right? Depending upon the friction, the mass will move or it will not move, depending upon the theta value. You keep on increasing the theta value more and more slope until some point the body will not move, and after that it will move. Okay, so we have to identify that angle up to which the body will not move is called as the angle of repose. Okay, now the angle of repose, right? We try to find out that's the value of alpha, right? Angle of repose alpha. So that alpha is always equal to the lambda which we have calculated earlier. Now the point is this. So if the theta value is less than alpha, right? This means block is stationary. Block will not move. Okay, if theta equal to alpha, right, the block is on the verge of sliding. The block might start moving at any point of time. All right, so that means the block is I can write, okay, it's on the verge sliding, and if theta is greater than alpha, right, block, this implies block slides, slides, slides with an acceleration, right? That acceleration A is given by the force minus Fl, limiting friction, divided by the mass. This is also equal to G into sine theta minus, this is mu, G into sine theta minus mu times cos theta. You can apply anything, right? Both will give you the answer. Okay, let's apply this and solve some problems. Consider the following diagram. Okay, let me copy this. Now, the values are given. It's the mass and theta values are actually given. The mass of body is 1 kg and inclination is given as 30 degrees. Okay, and it is given in such a way that, right, the mass of this body is 1 kg and this particular mass is about to slip, right? The question is to find mu if the body is about to slip, right? You just see what is about to slip. About to slip means on the verge of sliding, that is theta equal to alpha, right? So this, in this particular problem, right, theta is given as 30 degree So for the above condition, theta should be equal to alpha. So alpha is also 30 degrees. This is what we come to know, right? So, but what is alpha? Alpha is actually lambda, right? Lambda is this, right? So for any problem, alpha is always equal to lambda. That is the angle of friction, right? So let's try to write that. For this given problem, alpha is equal to 30. So, but lambda is also always equal, not lambda. Yeah. So lambda is given, sorry, my mistake. So the lambda is what I'm supposed to find. So lambda and A is, so you can see that lambda and alpha are same. So I write lambda equal to alpha equal to 30 degree. By using the equation for angle of friction, I know this, right? So what is mu? The coefficient of friction, that is mu is equal to tan lambda. So this is equal to tan of lambda is 30 degree. Tan 30 is equal to 1 by root 3. Okay, this is the required